So, now that we have all of this here, let us try to summarize it for the power regulator that we built. So, what was the input voltage range? Input voltage range was 3 to 4.2 volt. So, we will roughly say this is min, this is max. We are preparing our specification table, right. Typical output voltage is, this is tip, 1.8 volt. Output voltage range 1.5 to 2.1 volt. Output voltage accuracy minus 0.7 to plus 0.7%, right. This I am going to tell you again that you should really look to simulate this on your own. Understanding the world of mass manufacturing is very important for an embedded system engineer. So, if you are looking to ship millions of units a year, if you are building a product that will ship in the millions of units per year, then it is very important as the person architecting that system to be confident that we are not going to have lot of loss in yield because of the way the design was done. Design needs to comprehend variation in components, the distribution of that variation, and make sure that we will still get a very good manufacturing yield when we go to large volume. Line regulation was I do not remember the number, 500, right, was 500 millivolt. So, the load regulation is 250 millivolt. The standby current was 360 milliamp. The load current, that was a specification for us, so that was 100 milliamp, and the short circuit current was 720 milliamp. So, now if you were to go to the market, pick up a linear regulator, open its data sheet and look at it, it will roughly have a table with the parameters like we have outlined here. Now, we have on purpose designed a very poor linear regulator. We have just used 2 resistors. So, it is not a big surprise that our specification numbers are not great. If you buy a well designed linear regulator, and we will through the course of these sessions understand how to do that, these numbers will be far better controlled. But before we get to a conversation of how to optimize the numbers, we need to know which of those numbers we should be optimizing. So, let us do some quick study to understand what do we like about these numbers, what do we not like about these numbers. So, what do we like about these numbers? If we look at the output voltage accuracy looks pretty decent. It is within a percent. So, the output voltage accuracy of plus minus 0.7% is acceptable. Other than that, I would say everything else is a red flag, that all the other parameters are really not usable in the context of a linear regulator. Line regulation of 500 millivolt, very high. I mean, when your input supply changes by 1 volt, you do not expect your output supply to change by 500 millivolts. So, that is an obvious red flag. Load regulation of 250 millivolt, again very high. When your load current goes from 0 to its maximum, you do not expect to see such a large variation. And we have chosen very low resistors. We have chosen 5 ohms. Even with 5 ohms, we have a high load regulation. On top of that, we also have an extremely high standby current. If your standby current is 360 milliamps and you have a 1000 mAh battery, then your from the time you shut off your device, in 2.5–3 hours your battery will be fully discharged. So, completely unacceptable. Short circuit current, now the standby current is already 360 milliamp. So, you would expect the short circuit current to be higher. We will not mark that as a red flag, maybe we will just put a question mark next to it. I think we have enough red flags to worry about even without that. So, load regulation, line regulation and standby current are all bad. Now, the other way of thinking about line regulation is to look at the output voltage range. So, the output voltage range is also not something that we can accept. So, the output voltage varying from 1.5 volt to 2.1 volt, which like I said is another way of talking about the line regulation, is also not acceptable. So, output voltage range is not acceptable, line regulation is not acceptable, load regulation is not acceptable, standby current is not acceptable. One of the things we have done is that we have worked with just the resistive divider. So, all of these parameters are intertwined with each other. You touch one, you will end up impacting the other. For example, let us say load regulation is 250 millivolt. I want to make it 10 times better. I want to make it 25 millivolt. What I can do is I can say I won't work with a 5 ohm resistor, I will work with a 500 milliohm resistor, right? And you can do that math. If you drop the resistance 10 times for our regulator design, the load regulation will immediately drop 10 times because it is just I times R. But the cost of that is that the standby current will increase by that same factor of 10x. So, each of these parameters are tied to the other in some way or the other. And what we want to do next is to see how do we build a regulator so that these dependencies are not present. That is what we will look at next. For me was that the standby current was high because I had to maintain a low output impedance. I have to supply 100 milliamp after all, which means I have to maintain a low output impedance. And if I have to maintain a low output impedance, the only way I can do that is if the resistance is small, or I have to decouple the resistance or the generation of reference voltages from the block that supplies the current, right. So, the way you would do something like that is to say, okay, I still want, let us say this is V in. What I am going to do is, first I am going to generate a 1 volt reference, right. I know that when it is 4.2 it will go to 1 volt, right, or we will do it for, when it is 4.2 it will go to 1 volt. Now, because this is only generating the reference for me, I am not too worried about its value, its output impedance does not matter. So, I am going to make that resistance very high. So, now if you look at it, it is 420 kilo ohms in series, which means that when V in is 4.2 volt, this is only going to take 10 microamperes. So, now I have at least got a handle over my standby current problem by saying that I will use this resistive divider only to generate the reference. Now, this reference I am going to supply to a amplifier, right. Now, when V in is 4.2, this Vref, this we will call Vref, right, is so when this is 4.2 volt, this will be 1 volt, right, and at that point I want 2.1 volt at the output. So, what I will do is I will make this let us say 200 kilo ohm, and this is 220 kilo ohm, right. So, it will make sure that this voltage now is when V in is 4.2, this voltage will be 2.1 volt. Now, let us put the signs for the op amp. We need negative feedback, the only inversion comes from the amp. So, this has to be negative, this will be positive. Now, we saw this with the battery charger also, and you have seen this earlier in the course as well, that now the output impedance is going to get become very small because the loop gain is going to come and help you. So, R out divided by 1 plus loop gain will be the effective output resistance. So, it will be a very small number, which means that now at least we have, just going back here, what we have managed to do is say that, okay, now I know if I have an amplifier, I can separate the load regulation problem from the standby current problem. So, I can now achieve a very low standby current while ensuring that the load regulation is good. So, now the 320 kilo ohm and 100 kilo ohm resistors do not come into play at all, when you talk about load regulation, because when you are talking about supplying current here, that current has no bearing or these resistors have no bearing on that current. One thing I should do for completeness sake is these are active circuits, so they need power. That power also comes from the battery, right. So, it is important to understand here that this load current, the change in load current, which is what drives load regulation, the change in load current is not impacted, or the change in when the load current changes, the change in the output voltage is not really related to the 320 kilo ohm and the 100 kilo ohm. So, the reference generation portion of the circuit is now isolated from the current providing portion of the circuit. So, load regulation can be very good while maintaining a very low standby current. So, in this case standby current will be let us say LDO, we keep it active at all times. So, it will take about 5 microamp through the 220K and 200K resistor and 10 microamp through the 320K and 100K resistor. So, we are talking a total of 15 microamp plus whatever standby current that the amplifier itself takes, which will be small. So, let us say another 10 microamp. So, maybe with a 25 microamp budget we can maintain this in standby. So, we have solved two of the problems that we were facing. Which two problems have we solved? Let us just go back to the table here. So, if you look at the table, now the way we have budgeted the currents, we said that the standby current will be maybe 10 microamp from the amplifier, 5 microamp through one resistor chain, 10 microamp through the other resistor chain, giving us a total standby current of 25 microamp, right. So, what was 360 milliamp and turning out to be a much a very large problem unless we further reduced unless we increased the resistor, in which case load regulation would have suffered, has been addressed through the use of the amplifier. Now, with the amplifier we were able to decouple the standby current problem from the load regulation problem. The standby current is now down at 25 microamp, and because the output current is now being supplied by an amplifier as opposed to being supplied by a resistor, the load regulation will also be much better. So, we are not calculating the load regulation again. It depends on how the amplifier reacts to current, but what we know for sure is that this will also be very low, because an op amp has much better ability to provide current than a resistor does. So, we have now addressed the standby current as well as the load regulation. Now, let us come to the other thing. How does line regulation look? So, suppose I went with a circuit like this, how will the line regulation look? So, let us say now V in went from 3.2 to 4.2. What will happen to V out? So, when V in is 4.2, we already calculated, it will go to 2.1 volt. What happens when V in is 3.2, right? So, this node, let us take some colors, let us go back to this color. So, when V in is 3.2 volt, this node reference will go to 3.2 divided by 4.2, which means this node is also at 3.2 divided by 4.2, and this will go to 3.2 by 4.2 into 420 by 200, correct. I mean, it is no different from the previous calculation, you would have probably realized that by now, but it is just essentially saying that V in went through one resistive division, then it went through 1 plus R2 by R1 amplifier. So, resistive division and then one multiplication. So, this gives us 3.2 by 2, which is 1.6 volt, which is no different from what we had earlier, which means that delta V out, what we will call, we call line regulation, is 500 millivolt, right. So, the line regulation, which is the variation in the output voltage when the input voltage changes by 1 volt, is still at 500 millivolt. one of the problems we were trying to address with the resistive divider was the fact that it had very poor line regulation. So, if you go back to the table, you can see that with our 5 ohm resistive divider, the line regulation was at 500 millivolt, right. And now, even though we have an amplifier driving the output, the line regulation continues to be at 500 millivolt, right. The line regulation really has not improved through our changes to the circuit, where we have now decoupled standby current from load regulation. The line regulation problem continues to persist. So, load regulation is very good now, standby current is very good now, but we still have to solve the problem of line regulation. So, if we were to generate the reference, and it is not hard to see, no, you see the reference voltage that is being given to the op amp is now directly proportional to the input voltage, which means how much, if the input voltage varies by a fraction by a percentage of x, the reference voltage will also vary by x percent, which means output voltage will also vary by x percent, right. Now, our output voltage is half the input voltage, that is why we are getting a line regulation of 500 millivolt. So, the whole thing is very simple to understand why this is happening. So, now what people do to get around this is to say that, okay, you should have the amplifier, and I am going to add one small element to the amplifier. Usually you have something here that you might not know what this is, but assume for now that it is an element that is capable of providing current, right. It is a MOSFET, but you assume that for the purposes of your class work, this is an element that is capable of giving current, and that element also has one inversion. So, if this node is positive, this node is negative. So, you have to comprehend that when you look at the overall feedback, right. So, now if I have an element like this, it takes care of the load regulation, right. Now, so this is my overall amplifier. Now, because there is one more inversion here, the op amp's terminals have to change, right. So, like I told you, from this node to this node there is an inversion. So, that has to be comprehended in the op amp. So, let us go back to the values we had earlier. What people do is use something called a band gap reference. Again, these are new terms for you, and you might let us not worry about what the term means for the purpose of this course. All we are going to say is that a band gap reference is essentially a voltage that is far more accurate than you would get if you had a resistive divider running from the input source, right. A band gap reference is a reference that uses certain properties of different diodes and transistors to be able to generate a voltage that is relatively immune to both supply voltage and temperature. So, it is something that is using the physical process or physical nature of the variation in some of these components, and putting them together in a way that makes it invariant to with respect to temperature. And given that it is dependent on physical parameters or physical attributes of materials, it really does not depend on the supply voltage, right. So, you would use a reference like this to be able to generate this voltage now, and you will quickly see that okay, if I am using this is V out. So, now if I were to use a voltage source like this to generate the band gap reference. Now, the band gap reference does not have any dependency on the input voltage, which means that my line regulation problem is now completely addressed, right. So, my line regulation now, if I were to calculate, and for the purposes of this calculation I am going to assume that I want a typical voltage of 1.8. So, let us just play with these numbers a little bit. So, let us say this voltage, reference voltage is plus 1 volt, right. So, now band gap reference for the purposes of our understanding means that Vref does not depend on Vn. We will work with that understanding for now. Let us not worry about how band gap references are built, how those voltages are generated. That might require more prerequisites than we have at this point. Our takeaway as embedded system engineers is, okay, if you have a band gap reference, it means that output voltage is almost golden, that it will not vary from the 1 volt that it is specified to be. We will operate with that assumption for now. So, what you will quickly realize is that, oh, if that reference is 1.8 volt, 1 volt, V out now, if this is 1 volt, then this will also go to 1 volt because of negative feedback. So, V out will be equal to 360 by 200 into 1 volt, which is 1.8 volt, right. And now it does not matter what V in is, right, whether if V in is 3.2 volt, V out is still 1.8 volt. If V in is 4.2 volt, V out is still 1.8 volt. So, the line regulation now is almost 0 or is 0. Why almost? In this case, line regulation is 0. So, now the only variation you get is now limited by, in some sense, the line regulation of the band gap reference. So, let us say the band gap reference has 1 millivolt per volt type of line regulation, that might now filter through to the output, right. So, using a amplifier to drive the load allowed us to separate load regulation from standby current, and having a band gap reference to generate the reference allowed us to achieve very low line regulation, right. So, now when you look at the most basic regulator, it will look something like this, right. So, that is where we will stop for now, and we will look at a linear regulator data sheet in more detail tomorrow.